All right, guys. Good afternoon, everyone, and I welcome you to the second interactive
Good
session of the
afternoon, sir.
course. Yeah, good afternoon, Santosh, and good afternoon to everyone present here. Sanvi, Kartik, good afternoon, everyone. I welcome you to the second live session of the course, Fundamentals of Conduction and Radiation. We had a good discussion the last week, the last Saturday, and we solved some very involving problems associated with the contents that you just saw in your video. Just one second. Okay. Yeah, so I was telling that so we solved some problems in the last week that was associated with the video lectures of assignment 1, and I think partly we will be dwelling in some problems of assignment 2 this time. But meanwhile, right, before I start this session, as I said, this will be an interactive session. So it just not me just speaking around and solving sums here. So I'll be happy like if you stop me at any point of time and ask your doubt related to the course of the things that we have learned so far, basically up to week 2. And then if you find any difficulties in the assignment that you are solved, I think you have just solved assignment 1 and you are supposed to solve assignment 2. So if you have any difficulties there, just feel free to just unmute yourself or type in the chat box and let me know. We will start off with the ones that we left in week 1. So before that, I will quickly summarize what we essentially did in the previous week, and then I'll take up your questions, and then we'll begin with the contents of this week. I hope this is fine with everyone. In the meanwhile, let me check if I started the recording or not. Um, yeah, I think it's recording. Okay. Okay, in the meanwhile, I'll just introduce myself. Most of you guys know me. I'm Raj Nandan from IIT Gandhinagar. I'm a PhD scholar in the discipline of mechanical engineering, and I'm in my third year of PhD. And I happen to be your NPTEL TA for this course, and I'm a PMRF and I enrolled for this fellowship in 2022. And this is much about me. I already said it in the first class, but for the ones who joined this time, this is just a brief bio of me. And with this, let's just quickly recapitulate what we did in the previous week, and then we will come up with your questions, and then we'll begin with the agenda for the second week. I hope this is fine with everyone. So what we did is we started the elementary concept. We started with the elementary concepts of conduction. We moved into convection and then radiations. Okay. Although I said that this course will be basically dealing with conduction and radiation heat transfer, but as I say, convection heat transfer is something that always go hand in hand with these two heat transfer phenomena. So we looked into something which is known as the heat transfer coefficient and all. So we began by solving a simple problem which deals in 1D conduction heat transfer, and we use something which is known as the infamous Fourier's law. And we looked into how this law actually works when we solve problems associated with 1D steady state heat transfer. And then we looked into the cases where the Fourier's law is actually valid. Okay, it's not that you can just use the Fourier's law as and when you find the heat transfer problem. It's not like that. So there are certain instances where this Fourier's law is valid. One of the important assumptions that this Fourier's law deals is this 1D steady state heat transfer. And then we solved this sum. This was rather a simple sum that we solved. It says that it says that the temperature difference between these two phases were given to us, and we were asked to find out the heat flux and then the heat transfer rate based on the fact that the thermal conductivity and the area of the material is known. One important bit of information, and or I would say one important bit of knowledge that we develop is that under what circumstances is 1D heat transfer valid. And we also learned that why this problem is essentially a 1D heat transfer problem and not a 2D or a 3D heat transfer problem. I hope this is clear with everyone. Again, if you have any doubt, you can ask me. Then we moved on to solve a similar problem where again the temperature at the two phases were given, the thermal conductivity is given, but now we looked into the fact that what happens if we insert a medium which has a very low thermal conductivity with respect to the thermal conductivity of the parent medium. For instance, if we use air in between these two glass panes, we saw that the rate of heat transfer significantly decreases. So we found out that if we use air in between these two panes, the rate of heat transfer came out to be very much less than the ones when we don't use air space in between these glass panes. Okay, so this is something that we saw, and a practical example where we learned that such kind of arrangements are used is in airplane windows, as you guys have rightly pointed out in the last class. And then we moved into something which is known as convection, which primarily consists of two phenomena: advection and conduction. Conduction typically takes place at the no slip plane, and then when the fluid moves due to its effect on viscosity, the mode of heat transfer changes from conduction to advection, and the couple manner of advection and conduction is known as convection. And an important parameter which we learned in this context is the is the heat transfer coefficient. We developed the unit, or in fact, we looked into the unit of this heat transfer coefficient. And the key takeaway of this exercise is that unlike thermal conductivity, which is a material property, heat transfer coefficient solely does not depend on the material. It depends on the material as well as it depends on many other factors like how fast the fluid is moving and so on and so forth. Okay. So then we solved a similar problem involving calculating the thermal conductivity by using Fourier's law. This we will not spend much time now because we already saw it. Next, we move on to something which is known as a variable thermal conductivity case. For instance, what happens if the thermal conductivity of a material varies along the spatial direction? Our task again was to find out the temperature gradient and the temperature profile. This is something that we saw, and we ended our discussion with solving. So this is not so this is a different problem, but yeah, we ended our discussion with solving a problem which involves the coupled effect of convection and radiation. Okay, so the problem was that there was a pipe through which steam was basically flowing in any direction. As you can consider, the surface temperature of the pipe was given, and the heat transfer coefficient as well as the ambient temperature was given. In addition to this, the emissivity of this pipe was also given to us, and from that we evaluated what will be the heat loss that is basically going to take place from the surface of the pipe to the ambient. Okay, the heat loss is, as you know, is will be now governed by two phenomena: convection and radiation, because we assume that the pipe temperature as well as the surface temperature and the temperature of the steam will be so they are basically equal, which means there won't be now any conduction heat transfer taking place from the material of the pipe. Rather, there will be now convection which will take place from the surface of the pipe to the ambient. And since the emissivity of the pipe was given, there will also be a radiation heat transfer taking place. Okay, so then we estimated what will be the heat loss, and this is something that we did in the last class. Okay, so I'll stop here for some time. This is just a brief summary of what we saw the last week. I just gave it such that it refreshes your memory of what we did. So I'll stop here for some time. As I say, I'll take your questions now based on like what we learned in the last week. If you have any questions on that, or if you have any questions on the assignments that you solved, this is also something that you can discuss. And if not, then we'll move ahead with the uh, contents of this week. I hope this is okay with everyone. I'll stop here. If you guys have any questions, you can ask me, or else we'll proceed. So could you I hope you are solving the assignment for the course. So could you solve the assignments? Can you give me a yes or a no? Like, how are you finding the assignments? Is it solvable? Especially assignment one. I think they have just uploaded assignment two, but I think we're on the verge of submitting, or I think we have submitted assignment one. So from the audience that I have, can you just let me know how is that going? Was it tough, or was it easy, or is the problems that we are solving really assisting you in solving the assignments? Can you let me know? Yeah, so I think we have three audiences here. Yeah.
Sir,
Yeah, go on.
can I tell something, sir?
Yes, sure.
Actually, fundamentally, I can understand, but
Yeah.
during calculation of the problem, it was very difficult for me. It is difficult
Okay.
for me.
So, okay, I understand. So, where are you finding the difficulty? Can you be more specific?
Actually, now at present, I am in the work spot, though. I could not
Okay.
show you my calculations also.
Okay. Okay.
So I am unable to show you actually.
Okay. But like, so, so if I'm not wrong, in the previous assignment, so there were
Yes.
sums like, so there were sums that involved, so there were some basic sums like this. Okay. So like, although the sums that we solve in these live sessions are not exactly the same that are there in the assignment, rather the problems on the assignment are a little bit simpler to the ones that we are solving here. But in practice, it's going to be the same. It's in practice, it is going to be the same way that we are dealing that so the way that we are dealing here in the interactive session, the same way you are going to be solving in the assignments that you are going to do. But if I am not wrong, so I think it involves using Fourier's law like this. So there are some couple of questions that involves the calculation of heat flux, which is essentially the same that we did in the last class. Okay, so if you missed the last class, I would suggest that, so I explained like thoroughly how do we actually tackle problems associated with the Fourier's law, associated with heat transfer coefficient, and the radiation problem that we solve. So what I would suggest, Santoshji, is like what you can do is so my sessions, so the sessions that we take every week, these are being so they are recorded, and you can find them in the course website. Okay, if you search NPTEL course, then the name of this course, and I hope you are enrolled in the website, so you can find that live session in the website. I would suggest you can go back to that session, okay, and see how did I solve, or how did we solve the problems involved in week one. Okay, and then this would be of your great help in solving the problems of assignment one. And for this week, like I'll thoroughly show you like how are we going to do. So is that okay, Santoshji, or like
Okay, 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 okay,
okay?
okay,
Yeah.
okay.
So
I'll,
uh, so so before beginning, as I said, these so the sessions that we are conducting right now and the sessions that we'll be conducting later on, they are recorded and they will be uploaded. So they will be uploaded right after the session ends. In fact, I'll do the upload and all these things, and then they will be shared in the website. You can visit the website, see. So in the website, you can see that I think after every week there will be this. I think there is, I forgot the name, but I think it's there's a tab which says live sessions recording and something like this. If you click that tab, in that tab you will be like diverted to a Google Sheet, and in the Google Sheet you will see all the recordings of all the YouTube links of the sessions. For instance, if you open the Google Sheet now, you will see the YouTube recording of session 1 and the notes that I have shared, that I have written. For instance, these notes that I have written, you will also find this in that sheet itself. Okay, so in that way you can revise and recapitulate. And if you miss, for instance, if by any emergency or by any chance if you miss the week, you can always go back and see what has been done in that week. Okay, I hope that is fine. So with this, if you don't have any other questions, and as I said, always feel free to just interrupt me at any point, because it's a live session, and that's why it's the sole intention of this session is the fact that there could be interaction between the learners who are enrolled in the course and a course member like me who will be taking the session. That's typically because in the videos you don't get to interact with the faculty, right? And that's why this is the sole purpose of these interactive sessions that take place in the course every week. Okay, so with that, let's get started. So in this, so we'll begin with the week two's contents. So in this week we will be dealing problems mostly associated with assignment 2. Okay, and as I said repeatedly that they are not exactly going to be the problems that are there in the assignment, then this does not serve the purpose, right? It's just me solving the sums for you, and then it's basically against the spirit of the course and the subject. Okay, so we'll not solve exactly the questions, but the questions should be very much similar, and fundamentally they will be very much like involved. And if you understand how these problems are being solved in this week, then you can go ahead and do you can very readily go ahead and do the problems in the assignments of the corresponding week. Okay, so with that, so in this week what we will do is we will now solely, so in the last week we gave a brief introduction on conduction, convection, and radiation, but from now on, yeah, Yes, Kartik, go ahead. Kartik, I guess you raised the hand. You can go ahead, or you can just unmute yourself and speak. I don't know, like Kartik, do you have any questions? Okay, I think it was by mistake. But anyways, if you have any questions, you can just write. If you are unable to speak or by some ways, you can just write it in the chat box, and I'll take your question as and when you write. Okay. Uh, I hope like I'm audible to everyone. But anyways, so we learned about the three modes of heat transfer, primarily conduction, convection, and radiation. But from now on, we will deeply delve into conduction heat transfer for at least the next couple of weeks, or more than that maybe. And then we will see how this mode of heat transfer essentially works. Okay, we will from so for instance today we will see deeply the Fourier's law, the so a prototypical examples we already saw in the last week, but today we will be learning extensively how to use the Fourier's law. There is a very famous equation which is known as the heat diffusion equation. I hope you have learned this in this week's classes. So we will try to understand the essence of this heat diffusion equation by solving certain examples. There is also a very famous term in heat transfer which is known as heat generation. And then while doing all these exercises, we will try to understand the problems in a more systematic way by following a control volume approach. Okay. So I'll come to the details of all these things when we solve the problems one by one. But in a nutshell, we are basically going to do these things today in a week two. Okay. If you have any questions on this, you can ask me, or else we'll begin with the solution of the first problem. Okay. The first problem is displayed in your screen. You can 1 second. So you can have a look at this problem. Anyway, I'll solve it for you, but you can have a look and try to think about, as Santoshji also said that you find it a little bit difficult to actually begin or actually trying to solve a problem. I will show you systematically how actually it is done, but at least for the first time, try to think about like what the question is actually trying to say, what they have so the datas what they have given and what they actually wants us to find out. Okay. uh, give a look. I'll stop for 2 minutes and then I'll explain you the question and then I'll show you how the procedure essentially works. Okay. And in the meantime, if you have any questions, you can ask me. Kartik, I think you raised the hand. If you have any questions, you can either unmute and ask, or you can write in the chat box. In the meantime, just go ahead, see the question once. All right. I believe you have just gone through the question at least once. So what this question says is that you need to assume a steady state and a 1D heat conduction through a symmetrical shape as shown in this figure. So this shape, can you tell me, is this symmetrical about this axis or it is symmetrical about the vertical axis? This is the first thing that I would ask you. So when it says it's a symmetrical shape, as you can see from the figure, can you tell me through which axis is it symmetrical? Is it symmetrical through this or through this? Can yeah.
X
Yes,
at the
axis.
central
Yes, yes,
center.
yes, exactly, exactly. So as Sanvi and Santosh said, so it's symmetrical about the x-axis. So we'll take for instance the x-axis in this direction. Okay. Now what they are saying is that assuming there is no internal heat generation, derive an expression for the thermal conductivity kx for this condition. The area of this shape varies as ax. So it says that as you can see the shape that the cross sectional area of this shape is varying. So for instance, if I pick this cross section, the area is not the same as that of this cross section, which means it's not a constant cross sectional shape that we saw indeed in the last class. So as you can see, we are adding complexities to the problem that we are trying to solve. Okay. So what this says is that now the area essentially varies with x, but to our fortune, as you can say, the area is essentially a linear function of x and it varies as 1 minus x. Okay. For instance, if I pick this as x1, the area at x equal to x1, can you tell me what this would be? And if I say this point is x1, can you tell me what is the area at x equal to x1? Yes, that's easy, right? All I'm saying is that if I pick this position of x as x1, x1 can be any arbitrary number. It could be 5 units, it could be 10 units, it could be anything that you wish. Okay. But what I'm asking is that if I pick x to be equal to x1, let's say my area would thus be 1 minus x1. Okay. And similarly, if I pick points here or if I pick points here or here, the area would consequently change as 1 minus of whatever the point that we are picking. Okay. But it's a linear relation. So in that context, the temperature profile is also given to us, which is basically 300 into 1 minus of this polynomial. Okay. And it says, so these are the important bit of information that you need to understand. The area variation is given. The temperature profile is also given. And it says that the rate of heat transfer, which we denoted it by Q, you may also remember it in the last class, is given to be equal to 6000, where A is in square meters, T is in Kelvin, and X is in meters. Okay. So this is given to us. So based on this information, just from these underlined quantities that I said, based on this information, what they are asking us to do is that they're asking us to find out what will be the expression of thermal conductivity as a function of x. So first of all, did you understand the question or not? That's my first question to the audience present here. Did you understand the question? Sanvi, Karthik, and Santosh.
Yes, yes.
Okay. So, okay, Sanvi. So what we will now do is, okay, can you tell me, so before me telling you the answer, can you tell me or can you suggest me an approach through which we'll basically be solving this, and any idea? So what should we do first? Yes, okay, Kartik. So can you just think of an approach? What should we do here? So just think, what can we use and what do we learn? Okay, Fourier's law. Sanvi is exactly right. So we will use Fourier's law, but exactly we'll be using Fourier's law only. But we will actually try to prove one thing, and from that on only we will proceed with the Fourier's law. Okay, and I'll show you how basically we need to do. So what I will do is I will take control volume. So I hope you are aware. So do you know what the control volume essentially means? First of all, there is a term which is known as control volume, and there is a term which is known as a control, or you can say, okay, let's not go into the other terms, but there is a term which is known as a control volume. So do you guys know what do you mean by control volume? Can you give me an idea what essentially a control volume is? Santosh ji or Sanvi or Karthik?
No, no additional
Yes.
energy interaction in that volume, I think.
Okay.
That may be within adiabatic some state. There
Okay.
is no interaction.
Okay. I would say, Santosh, you are partially right. But the term that you have used is that the energy, okay, a fixed is enclosed in a mass and energy makes sense. Yes. Okay. Sandhi's answer, I would say it's little bit more correct, but I'll try to explain to you, Santoshji, what essentially is a control volume before actually trying to solve this problem. So Sandhi says, so what you says, I would say it's wrong. It's partially correct. And what Sandhi says is that a fixed region enclosed by a boundary, the mass and identity may change. Yes. I think act as an open system where mass and energy leaves. Yes. So that is precisely the difference. What Santosh ji I mean you kind of missed. So what you says is that there won't be. So for instance, what I will do now is I will choose a control volume which is basically like this. Okay, which is enclosing the surface, the form of the shape. Okay, that we are considering. So for instance, this is the control volume that we are choosing. Okay. Now, what Santosh said is that he said that there won't be energy that will be entering or leaving through this control volume. But that is not exactly the case, Santosh. So if you are considering a control volume, as we will see very shortly, there can be transfer of energy. Okay. Under a very special case, this energy transfer will not take place. And by means of energy, in this course, we will always talk about heat transfer, unless and until we have any other forms of energy. Okay, so when I say energy in this course, at least there are essentially many forms of energy. For instance, like whenever a fluid flows in, it carries whenever a fluid flows in with some velocity, it have a kinetic energy. Okay, if there is some height, it can have a potential energy, and based on all these energy interaction, there is also some form of energy which are known as energy in transit. For instance, heat and work is something which is known as energy in transit. Okay, and in this course, by the context of energy, I'll always stick to something which is known as heat transfer, the one that we are studying here, and neglecting all other forms of energy unless and until it is stated in the question. So the first point is that when I talk about energy, which means heat in this context, Santoshji said is that there cannot be energy interaction in through this control volume. But this is only a special case where you are correct. And that special case is known as an adiabatic condition. And in this context, and in this problem, when I say that energy transfer cannot take place through a boundary, which means that if I kind of insulate, okay, if I kind of insulate these boundaries, okay, then heat transfer through these boundaries will not take place. Okay, did you understand my point, Santosh, or not? But there could
Yes,
be,
sir, I understand.
yes,
Understand.
but there could be possibilities of heat transfer taking place between these two phases, right? And in fact, if we are considering 1D heat transfer, these two phases are bound. So heat transfer between these two places are bound to take place. Okay, so is this clear?
Yes, sir. Yes, sir.
So when I say it's a control volume, it does not always mean that heat transfer will not take place. It can take place depending on the nature of surfaces that we have. Okay. For instance, these surfaces, as you can see, these are insulated. And because of this reason, heat transfer is solely going to take place in the x direction and not in the y and z or all other directions. Okay. So for clarity, I would say this direction is y, and what now we will do is so there is a very famous law which is known as the law of conservation of energy. So what we will now do is we'll apply the law of conservation of energy in this control volume. The reason why we choose the control volume is that all the laws that we learned, for instance, the law of conservation of mechanical energy or the law of conservation of energy, these are applicable so long as we choose a control volume on which we are applying these laws. Okay, so now what we'll do is although the answer to this problem is very simple, but this is a systematic way of essentially doing this problem. So what we will now do is we will apply energy balance in the control volume. Okay, so if I now apply energy balance, can anybody tell me what basically the energy balance look like if I apply this energy balance in? So for instance, forget about this control volume, but can you tell me what's the energy balance or the law of conservation of energy says? Can you tell me? So my question is, forget about the control volume that we are considering now. What does the law of conservation of energy in this nature says? Like, can you give me an idea? Yes. Yes, Sanvi says that energy in minus energy out plus energy generated is equal to the energy rate of. Yes, I got what you were saying. So I'll explain to the audience what Sanvi said. So what Sanvi says is that if I now apply the law of conservation of energy in this control volume, then it's very simple. It says that the so what is said is that, okay, I'll write and I'll explain to you. So what this said is that the rate of change of energy that is coming out inside the control volume minus the rate of change of energy that is going out from the control volume plus the rate of change of energy or the rate of energy that is generated inside the control volume is equal to. So in steady state, this, can you tell me what this should be equal to, Sanvi? Oh, I already wrote, but yeah, okay, I already wrote, but in steady state, this should be equal to 0. So did you understand this energy balance in this control volume or not? Santosh, can you tell me, like, did you understand what did I wrote basically here?
Yes, sir. Yes, sir. I
Okay,
understand. Yes, sir.
yes. So I'll repeat once again, and of course we'll be going very slowly in this first question. So what we did is we picked out this control volume, and this is typically the reason why we are choosing this control volume. The sole reason is that for applying this energy balance, we need a space, right? And where we are applying this, we are applying this on this form. Okay, we are applying this on this form of the object, and hence we need to choose a control volume, and our control volume is the object itself. Okay, and in that object
Sir,
we
in this
apply.
problem,
Yeah,
sir,
yeah.
in this problem, energy generation is zero, na?
Yes, and yes, exactly. We'll come to that. We'll come to that. But
Okay.
this is typically the law that that actually says. Okay. Now, what we will do is, as Santosh has rightly pointed out, if we read the question carefully, it says that assume steady state one-dimensional heat transfer to the system, and it also says that assuming there is no internal heat generation. So, can you tell me which term drops out in this equation? I'll name this as equation 1. Can you tell me which term drops out? Yeah, go on. Yes, Santosh, you said the answer.
Yes.
So it's energy generation, right? That's what you said. So this means this term essentially drops out. I mean, so far so good, right? I mean, you were with me, right? You understood what I just said.
Sir, again, pardon, please, sir.
Yeah, so I'm saying that, can you understand why did I drop this term out? That basically because it's given in the question that in the space that we're considering, there is no energy generation.
Already,
Okay?
already it has written in the question, na, sir?
Yes,
Yes, sir.
exactly. Which means this energy balance essentially simplifies to E dot in minus E dot out, and this is equal to 0, which means E dot in is equal to E dot out. Okay. This is essentially very important to us. You know why? So, since there is no energy generation, what this says is that whatever the energy or whatever the heat that is coming in is equal to the heat that is going out. Okay. And this is typically the reason why your rate of heat transfer for this problem is constant and it is equal to 6001. Okay. So, that's why since energy in is basically equal to energy out, this means that the rate of heat transfer is constant. Okay. So can you infer this? Like, did you understand what? So applying the energy balance, we inferred that the rate of heat transfer for this problem is constant. Okay, and it says that this Qx, the rate of heat transfer, is now given to be equal to 6001. Okay, and now what Sanvi essentially said, that we will now use the Fourier's law, which says that the rate of heat transfer is related to. So can you tell me what's the Fourier's law here? The rate of how is the rate of heat transfer related to something which we learned it in the last class? Did you get my question? So what I'm saying is that from the energy balance, we found out that the energy in will be equal to the energy out, which means that this rate of heat transfer will be constant in this control volume. Okay, and now this constant has, so what do we require? We require thermal conductivity, right? So as Sanvi said, we need to now use the Fourier's law to find out the thermal conductivity. Now, what exactly is
Sir,
the Fourier's law here?
ex-
Yeah, Santosh, go on.
excuse me, sir. Sir,
Yeah,
actually, I am leaving. There is some urgent work in the work spot. Huh?
yeah, it's okay, it's fine, it's
Sir,
fine.
okay, sir. Thank you, sir. I will listen the recorded class. Okay.
It's
Thank
okay,
you,
it's
sir.
fine. Yeah. As Sanvi said, it's basically equal to K, which is the thermal conductivity, times the area times dt by dx. Okay. All right. So now we just need to solve this. Basically, it is 6000 and this is equal to minus K. Okay. And remember, this area is also a function of x. It's also a function of x and it is given. So your a of x is given to be equal to 1 minus x. And dt dx you actually need to find out. So how do we do that? So that's very simple because you are given the temperature profile, okay? So T as a function of X is given, which basically looks something like this. So it is 300 into 1 minus 2 times X minus X cube. So from here, you need to evaluate this dt dx. So based on this, the dt dx would be what? It would be just 300 minus 2 minus 3x squared. Okay, so this is going to be your dt dx. So now what you need to do is you just need to substitute this dt dx into here, and then if you do the math, you will get your thermal conductivity Q of x to be equal to 20, sorry, yeah, so it will be equal to 20 by 1 minus of x into 2 plus 3x squared. Okay, so you can check it out. It's very simple. So you will get the thermal conductivity as something like this. Okay, so this is what the question has asked us. So as I repeat, the important bit of the question is essentially not calculating it with the Fourier's law. I know it's the crux of the problem, but it's understanding that why the rate of heat transfer is constant and it's not essentially varying along along the x direction through which we are considering. Okay, and also you need to understand, as we have already seen it in the last class, why this is a 1D heat transfer and it's not a 2D heat transfer. That's typically because these phases are essentially insulated, which means the only way heat transfer can take place is in the x direction, which is basically this. I'll ask an important question here, and this question would be the basis on which the second question that we are going to see is that we calculated that the rate of heat transfer is constant. That is typically because if I apply the energy balance inside the control volume, we got that energy in is basically equal to energy out. So there is no way through which the rate of heat transfer could be a function of x. Okay, but can you tell me, will heat flux be constant, or it's going to be or it's going to be a function of x, or in other words, will heat flux be a constant or not in this context of the problem? Can you tell me? So my next question is, think about it. So my next question is, although we have solved this problem, the question is, sorry, will q double prime of x, which is the flux by our notation that we have used, be a function of x or not? Can you think about this? So I hope the question is clear. So we established that the rate of heat transfer is constant, and we saw how the area essentially varies. So based on this, use the fact that how the flux and the rate of heat transfer is related, and try to come out with the answer that will heat flux be a constant or it will be a function of x. Think about this. I'll wait for some time, or else I'll just say the answer. But yeah, but this will be helpful when we look into the next problem that we are going to solve. But anyways, the unit of K already we know this watt per meter Kelvin. Okay, so I'll tell the answer. It's very simple. See, so how do we relate the heat flux and the rate of heat transfer? Because we already know the information of the heat transfer, right? So we know that the rate of heat transfer in x direction is basically equal to the heat flux, which we denote it by double prime, times the area, right? Yes, sorry, didn't. Yes, exactly. Sanvi, you are absolutely right. The rate of heat flux will not be constant. And in fact, the rate of heat flux, as you have rightly pointed out, would be the rate of heat transfer divided by the area, right? So we know and we have established that by the law of conservation of energy, we have established that the rate of heat transfer is constant, which means this is just a constant. And area, we know it's varying as 1 minus x, right? Which means whenever x increases, okay, whenever x increases, ax will drop, and if ax drops down, heat flux will essentially increase. Okay, so this is essentially how the rate of heat transfer varies. But yeah, you are exactly right that the rate of heat transfer will not, sorry, the heat flux will not be a constant, although the rate of heat transfer in this problem is a constant quantity. Okay, that's very good. So based on this, I hope this problem is clear. So based on this, we will solve a similar problem, and here we'll be much more clear on how this flux quantities or this rate of heat transfer and thermal conductivity essentially varies. And in this problem, I'll give you some time to read this problem. And here also we'll be using a similar analogy to solve for the like quantities that are being asked here. Okay, so I'll stop here for some time. Uh, we have finished solving the first problem. If you have any doubt on that, you can ask me, or else we'll solve this or we'll solve the second problem. But like I'll give you some time to read or to go through it, and then we will see how this goes on. Okay. All right. So I hope you guys have just uh, go through this question. So what is said is that a solid truncated cone serves as a support for a system that maintains the top truncated face of the cone at temperature T1, while the base of the cone is at temperature T2. What it says is that this surface of the cone is at temperature T1 and its base is at temperature T2. Okay. The important information that we know as and also as you can see in the screen is that this T1 is greater than T2, which means, can you now tell me what is the direction of heat transfer? Is it in the positive x-axis or it is in the negative x-axis? This is the first thing that we always try to that we should always try to figure out from a heat transfer problem, is that given the temperatures, and if we know the temperature, at least try to find out what will be the direction of heat transfer. Okay, so can you tell me based on this information what will be the direction of heat transfer? That's an easy question, right? So will it be in the positive x-axis or will it be in the negative x-axis? Given that my x-axis is this direction. So it's simple, right? So as I have already said, the top face is at temperature T1 and the bottom face, oh sorry, yeah. So the bottom face is at temperature T2, okay. And it says that this T1, which is this temperature, is greater than T2, which means now can you tell me what will be the direction of heat transfer? Will it be in this direction or will it be in this direction? Or in other words, will it be from T2 to T1 or will it be, yes, positive? Yes, you are essentially right. That's true. Because yes, that's true. That is simply because it's very simple. So as I have said, heat transfer always takes place if uh basically for an 1D heat transfer to take place, it always take place from a phase where temperature is higher. So T1 is higher. So this means this will be the direction of heat transfer. Okay, that's well and good. Now what they're saying is that based on this information, the thermal conductivity of the solid depends on temperature according to the relation with this, where A is a constant and the sides of the cone are well insulated. This is similar to the last problem that we said that these sides are insulated, which means if I now pick this as my control volume, as we have done it in the previous problem, if I now pick this as my control volume, okay, this means that heat transfer cannot take place from these sides, which renders the fact that it's a 1D heat transfer again. And similarly, if we apply the law of conservation of energy here, it again boils down to the fact that energy in is equal to energy out, since there is no energy generation here, as you have rightly pointed out in the last problem. Which means that in this problem also, we can be rest assured and write that E dot in is equal to E dot out. Okay, and the essential conclusion of this lies in the fact that the rate of heat transfer will be constant, which means again Qx is equal to constant. And this is the first question that this problem is asking. Do the following quantities increase, decrease, or remain same with increasing x? So the first problem, as you have already seen, that the rate of heat transfer Q of x is constant. So Q of x is constant and it remains same. Okay. So that's the easy part. So now tell me, based on this problem and the problem that we learned, is that what happens to the heat flux? Okay. So next we will look into we'll look into the heat flux. So try to relate the rate of heat transfer and the heat flux by the quantity that we just saw. Okay, and tell me what happens. So does heat flux increase? Does heat flux decrease? Or it just remains the same? So can you tell me? Yes. So this is simple, right? Take a look at the shape. Take a look at what happens to the area when you move in the positive x direction, and then try to come out with what happens to the heat flux. This is simple, right? It's very simple. So yes, heat flux will decrease. Yes, you are absolutely right. Heat flux will decrease. The reason is, so can you tell me what's the reason again? Why heat flux will decrease? Of course, the reason is again simple. I hope you understood it. So it's the fact that, yes, area increasing. That is absolutely correct. So the fact that your flux is basically equal to the rate of heat transfer divided by the area, and you know that this bit is constant when you move along the positive x direction. You know that this area is essentially increasing along the positive x direction, which means this term, your heat flux should decrease because this is in the denominator. So this should decrease as we move along the positive x direction. Okay. I hope so far you are on the same page with me. So this is rate of heat transfer here on the first one. And this is heat flux. Okay. Now we move on to the third part. So what the third part says is that what happens to the thermal conductivity. Okay, this is also simple because they have already given to us the relation of the thermal conductivity. Okay, it says that for the material, the thermal conductivity is a function of temperature. Okay, so what it says is that the thermal conductivity is some K naught minus AT, where this A, as you can see, this A is a positive constant, which means this A is positive. Okay, and I think K naught you can also take to be positive. So you can also consider A and K naught to be positive. Okay. So based on this fact and the relationship between thermal conductivity and temperature, can you tell me what happens to the thermal conductivity? Will it remain the same? Will it increase or will it decrease when we move in the positive x direction? Think about it. So the key point here is that you need to think about how the temperature varies when you move in a positive x direction, and that you have already said in my first question when we figured out what is the direction of heat transfer. Can you tell me? So this is simple, right? See, when you move in a positive x direction, our temperature. So recall that this T1 was at a higher temperature. Yes. So this T1 was at a higher temperature. Okay, and this T2 is at a lower temperature. Okay. I think Minesh just joined. I'll be briefing you, Minesh. So far what we did, but I'll just finish this sum and then I'll just brief you so far what we did. Okay. But yeah, so the thing is, we saw that this phase was at a temperature T1, this phase is at a temperature T2, and we know that T1 is greater than T2, which means when you move in this direction, what happens with temperature? Does it increase along the positive x direction or does it decrease along the positive x direction? Yes, can you tell me? It's simple, right? Yes, exactly. Temperature decrease. That's so it's very simple because this phase is at a high. This phase is at a higher temperature. When you move in this direction, obviously your temperature has to decrease. Okay. So if you know that when you move along the positive x direction, your temperature decrease, then what happens to K? K increase or decrease? Yes. No. I think you. So that's so. See, if this is constant, and if this is constant and positive, and if temperature decrease, okay, this should increase, right? Because this a times t will decrease and it's a minus sign, right? So your thermal conductivity should increase, right? It's obvious from this relation, right? Did you get it, Sanvi? Yes. Okay. So it's very simple. Just observe. Yes. Okay. No, it's fine. It's absolutely fine. Ah, so it's very simple because your temperature decrease. Okay, it's K naught minus AT, and your signs of K naught. So obviously, it is subjected to the signs of K naught and A, and we have take it for consideration that K naught and A is positive, which means that if T decreases, your K has to increase. Okay, so your thermal conductivity increases when you move in the positive x direction as your temperature decreases. Okay, So that's the third part. All right. Now, so that's the third part. Okay. So now we'll doing the final part. So can you tell me what will be the magnitude of dt by dx? So will dt by dx, I'm saying in magnitude because when we use Fourier's law, there is a negative sign if you remember. Okay. And dt by dx essentially will come from the Fourier's law. I think you have hinted to this before also. Okay. But let's not consider a minus sign. And that's why I'm telling that what will be the magnitude of dt by dx along the positive x direction. All I'm saying is that will it increase, will it increase along the positive direction, will it decrease, or will it just remain the same? That's the next part, or and the last part of the problem. Okay. Yes, Mines says it will decrease, and Mines, you are absolutely right. Sanvi, can you think of it? Is Mines is right, or like can you come up with an argument why dt by dx decrease? Yes. So from where did we conclude that dt by dx decrease? Can you tell me? So what do we need to use? I just said to you, we need to use the Fourier's law, right? So when we use the Fourier's law, it says that your heat flux is equal to minus k times, of course, this k is now a function of temperature, into dt by dx. Okay. And when I say magnitude, this means I can write that your heat flux is proportional to k times the magnitude of dt by dx. Okay, we will not consider the minus sign because it will be absorbed in the magnitude of dt by dx. Okay. Now what do we know? We know that now we know that this thermal conductivity essentially increases when you move along the positive x direction. Okay. And so this we have already calculated from here. Okay. We say that when you move along the positive x direction, your thermal conductivity will increase. Okay. And we also said that this heat flux will decrease when you move along the positive x direction, typically because your area increases when you move along the same direction. Okay. This means your heat flux will now decrease. So for this equality to holds good, okay, your dt by dx should decrease. Okay, if dt by dx also increase, there is no way your heat flux can decrease. Okay, but that is not possible because your area essentially increases with x. So this means that your dt by dx should decrease, as you have rightly pointed out. Okay, so your dt by dx should decrease. So I hope this is clear to you. Can you tell me one more thing? So why did we not consider? So is the minus sign here important or not? Or like why did we not consider the actual magnitude of dt by dx and just consider the fact that we are just interested in the mod of dt by dx? Can you tell me? So think about this and tell me like in the next class. That's okay. Uh, we have we have essentially like came up with what dt by dx would look like. But think about it that is this equal to the fact that minus dt by dx will also decrease with x? This is something that I'll ask. I'll leave for you to think about it. Okay. But in principle, yes, dt by dx will decrease, as you have rightly pointed out, when you move along the positive x direction. Okay. So I hope this is clear to you. So this is the second question, which was bit similar to the first question. So Mines, just for a briefing, what we did is we tried to solve conduction heat transfer problem here. We solved the problem, okay, using the Fourier's law, establishing the fact that for a truncated body where area essentially varies along the length, we use the control volume approach to argue that when there is no heat generation inside the control volume, your rate of heat transfer has to be equal to constant when we are in the limit of 1D heat transfer problem. Okay, at least in the limit of 1D heat transfer problem. Okay, so what we did is we established that and then we figured out the expression for thermal conductivity in the first problem, and in the second problem we did some argument that if we know the surface temperature of phases, what will basically happen to the rate of heat transfer, the heat flux, the thermal conductivity, and the temperature gradient, which you just now saw. So these are the two problems that we solve. Okay, if you have any questions on this problem, I'll stop here for some time, and then we will solve a very important problem, which is the third problem. Okay, and we'll take some time in solving this problem because it's a very important problem. There are problems similar to this in your assignment as well. Uh, but yeah, before solving that, If you have any questions, you can ask me. I'll stop here for some time. So up to this, is it clear to everyone, Manish and Sanvi? Like, is it clear? Okay, okay. Yes, Manish, you have a question? Yes, go on. I'm sorry, it's Minis. Okay, Minis, go on. Do heat flux is having using of E by M? I mean, you say you so unit. Okay, so you are asking what will be the so do heat flux is having So you are asking the unit of heat flux. All right, that's something that we discussed, right? So you will itself tell the answer to me when I write it. Okay, so we know that the rate of heat transfer is equal to the area multiplied by the flux. Okay, let's say we are considering the rate of heat transfer in any generic nth direction. Okay, so tell me what is the unit of rate of heat transfer. So what is the unit of so can you tell me what is the unit of heat? Yeah, it's watt exactly. So the unit of heat is joule. When I speak about rate, it becomes joule per time, it becomes joule per second, and that's why it becomes watt. Okay, and what is the unit of area? Can you tell me? Meter square, right? So then tell me what is the unit of heat flux? Watt per meter square, right? So that's what so it's not watt per meter, it's watt per meter square. So did you get what you were asking for? Okay. So all right. That's good. So I hope you got your answer. Uh, okay. So we'll try to understand the third problem. I hope you don't have any. So the first and second problems are very important problem. It actually give you a feel of quality. So it actually gives you qualitatively a feel of how 1D heat transfer essentially take place in tapered bodies. And also it's a very important conclusion that although your rate of heat transfer is constant, typically because there is no energy generation and you are considering one-dimensional heat transfer, your heat flux essentially varies. Okay, and people fails to distinguish these two important conclusions. Okay, mostly in in these kind of circumstances. Okay, so with this, well, yeah, go ahead, Minis, go ahead. You can you can ask more than one more query. Yeah, but in the assignment, they are asking the heat flux with unit of Kelvin. So K by M is what you are saying. So K by M is basically Kelvin per meter. So can you, but in the assignment, they are asking the heat flux in unit of Kelvin per meter. Kelvin per meter is basically, is that heat flux? That's not heat flux, right? Kelvin per meter is temperature gradient, right? Okay. So question assignment 2, question 8. Okay. I'll have a look. Okay. Maybe they did it wrong. And if they by some mistake, if they wrote it wrong. Okay. So there's the question. Okay. At the right one is. Okay. So I think, yeah. Let's look at the question. It says that a plain walla with thickness itna, and so they have given you thermal conductivity itna, if the less than itna, okay, then the heat flux. Okay. So I think that's a mistake. Okay. So it's a mistake in the printing. It should be, yeah, it has to be watt per meter square. Yeah. So this Kelvin per meter is wrong. That's the unit of temperature gradient. It has to be watt per meter square. But other than that, I think, see, I don't think you have a problem in giving the answer to this. That is because you need to enter it numerically, right? You don't need to enter the unit, right? Is it correct? Okay, yes, okay. Okay, it's fine. But it has to be watt per meter square. Yeah, you are exactly right. It has to be watt per meter square. I'll post it in the discussion forum also that it has to be watt per meter square. It's a typo basically. So yeah, you are right. Okay, all right. So now let's have a look at the third problem, and we will solve this problem very slowly and very systematically. And of course, you will also appreciate the beauty of this problem. So what it says is that again, it's a one-dimensional plane wall of thickness twice L equal to 100 meter, which means you can take the L to be equal to 50 each on two sides. But now it says that it experiences uniform thermal heat generation of Q dot, which is equal to what? 1000 watt per meter cube. Okay. And it is being convectively cooled at the two faces, which are at plus minus of 50 meter, by an ambient fluid having T infinity equal to 20 degrees Celsius. Okay. So if the steady state distribution of the wall, that is the temperature distribution, is given, which is basically equal to this, where A's and B's are 10 and 30, these are given, then what they're asking first is to calculate the thermal conductivity of the wall and the value of the heat transfer coefficient. All right. So I'll draw the schematic of this problem. Okay. I'll draw for you the schematic of this problem. And then we will solve it. So what this says is that, let's say this is my one axis. And since it's a 1D heat transfer, we'll consider this axis as my x-axis. Okay. And these faces, we will assume it has some temperature. Okay. The temperatures are not given, but the temperature profile is given. But this slab, as you can see, it is being cooled. Okay. So it is being cooled by a fluid which is basically flowing here. Okay. So there is a fluid that is being flowing here. Okay. And the slab is being cooled by this fluid. That is the first information that they have said to us. And secondly, what they have also said is that the ambient temperature of this fluid, they are saying it's T infinity, is equal to 20 degrees Celsius. Okay. So the same fluid is in this direction, which is also equal to 20 degrees Celsius. And there is a heat generation, which is basically given by Q dot in this slab. Also, what they have said is that the temperature profile T as a function of X is equal to A into L square minus K square plus V. Okay. So this is something that they have said, and this Q dot, the magnitude of this Q dot is equal to, so they have said it is 1000 watt per meter cube. Okay, it's 1000 watt per meter cube. Okay, based on this information, what they have asked us to find out is the thermal conductivity, which is K. Okay. And secondly, the heat transfer coefficient, which is H. We all know by now what's the heat transfer coefficient is. But yeah, these are the two things that they have asked us to find out. All right. So now, yes, I think we have, okay. One more thing, this length is basically equal to 100 mm, which means that in one part, this length is equal to 50 mm. Okay. And this 100 is what they have said is as 2L. All right. Okay. So I hope the question is clear to you. I'll wait again for some time just for you to be like familiarized with the question, and then I'll ask you a couple of questions before essentially solving it. And I think you should answer me these questions. Okay. Or at least try to answer these questions. All right. Let's get started. Okay. So first of all, tell me that if I happen to draw, I'll just remove this dimension. Okay. Just to make the picture a little bit clear. So if I take a cross section here, and I know that my direction of heat transfer is in the positive X direction. Okay. And if I take a section here or anywhere along the slab as we just take, can you tell me if I draw the temperature profile? So I'll just draw two temperature profiles here. Okay. This is, let's say, one profile. And let's say I'm drawing another profile. Or I'll okay, I'll draw some profiles. Okay. So this is one profile. This is one profile. Okay. And let's say I'm drawing one more profile here. Okay. Let's say I'm drawing something like this, something like this. Okay. So now you guys need to tell me which of the temperature profiles did I draw is essentially correct and it reflects the temperature profile that is given in your data. And this will serve as a very important exercise for you to essentially solve the problem. Okay. see, solving and all will do, but physically you must have an insight of how these things work, okay? And that is basically precisely the fact that why we are having to learn, or why we are essentially doing this exercise here. So what you need to tell me is which of these two profiles are correct, or which of these three profiles are correct, or are all the three profiles correct. I'll just say this is symmetric, but this is not symmetric, okay? Sure. And as I'm just reiterating, these are temperature profiles, okay? It just shows how temperature distribution takes place inside this slab. Okay, can you give it a try? Which of these are correct? 3. Sanvi said is 3. Okay, 3 is correct. So there is one answer which says 3 is correct. Minius, do you agree with her, or you have a different answer? Think about it. We'll go very slowly. Think about it, and so I'll give you a hint. Okay, what makes you think that 3 is correct? Okay, so you are thinking that this phase is at a higher temperature and this phase is at a lower temperature, and heat transfer is essentially taking place in this direction. Okay, so all the problems that we did, it resembles that profile, but there is a twist in this problem. Okay, and that's the reason why I'm coming up with this question. So Mines, can you give it a try, or Sanvi, do you want to rectify your answer? 3 is essentially not the correct answer. Do you want to rectify? See, the hint is there is a heat generation inside this slab, and whatever the heat that is being generated, it is getting dissipated into the ambient, and which is being cooled by the flowing fluid. So try to think about that at what portion of the what at which position in the slab there will be maximum temperature, or at which cross section in the slab there would be this maximum temperature. Will it be on this face, will it be on this face, or will it be on this face? uh I'll just wait for you. Can you think about this? See, the correct answer to this is, yeah, before, so do you want to give it a last try before me telling you the correct answer? All right. Just give it a try. I mean, what's wrong in trying it? At max, we will not get the answer, but what's wrong in that? Just give it a try. Mines, do you want to give it a try? Will it be 1, 2, or 3? I said 3 is not correct. Okay. I'll give you one more hint. I said you 3 is not correct, which means it should be either 1 or 2. Now, try to understand the direction in which heat transfer is taking place. Okay? Is it taking place from the slab to the fluid, or from the fluid to the slab? Okay, I'll tell you the answer. See, the correct answer to this is this temperature profile. Okay, so this is the correct answer. Okay, and these are essentially wrong. This is wrong, and this is wrong. See, the problem is very simple. Okay, there is a heat generation that is being taking place in this entire slab. Okay, so how much is that heat generation? That is 1000 watt per meter cube. So just think of it something like this. There is a slab, and in that slab, by some mechanism, you are producing heat. Now, when you are producing heat, this slab, what they will do is they will try to dissipate this heat. Okay, so when they try to dissipate this heat, what the slab will do it, whenever there is this heat generation that is being taking place, it will try to dissipate its energy to its surrounding by means of heat transfer that we all know. Okay, and then when doing so, the heat that will move out from this slab will be in these two directions. Okay, so what it's like, whatever the heat that is being generated, it will try to move out from these two directions. Now, why this profile is not correct? Because heat transfer is taking place from the slab to the ambient, which means that the slab has to have a point where the temperature is essentially highest. Okay, now this is the point where you can see the temperature profile reaches its maximum. Okay, which means this is the point which should have in principle the highest temperature, and it must have, right? That is simply because, see, another way of putting this forward is that substitute x equals to 0, and you will get t of x to be maximum at when x is basically equals to 0, and in all other subsequent x's you will get this temperature to be less than to that of the point where x is, as x is basic to 0, which means x equal to 0 is a point of maxima for the temperature profile, and now it is dissipating heat to its ambient. Okay, so the only way by which it can dissipate this heat is of course by conduction, but it should symmetrically distribute this heat because this point is exactly symmetric from these two faces, which means that if the same fluid flows through the either of the faces, these 2 points must have the same facial temperature, which will be lesser than the temperature at the point x equal to 0. Is this clear or not to everyone? Sanvi and Mines, is this clear or not? And this argues the fact that the temperature profile that I draw by the name 1 is correct. Did you get what I just said? Uh, Mines and Sanvi, or do you want me to repeat? I don't know if it's a yes or a no. Are you with me? Like, did you understand what did I say? Okay, I hope you guys understood it. But anyways, I will. If you have any doubts, okay, I'll be happy to repeat it. But anyways, we'll proceed with the problem. I hope you have understood why the temperature profile 1 is correct. Okay, so now that's not the task that we want to do. So what we need is we need to investigate the value of k, and we need to investigate the value of h. Okay, so then what do we do now? Okay, so can you tell me now how do we find this k and h, given that we know the temperature profile, we know the value of this heat generation? Okay, so I'll rub these lines. I just rub these lines because these are not correct temperature profiles. So did you guys understood it? I mean, is this an yes or a no? If it is no, I'll happy to like explain it again. But this is a very important concept, okay? And you must know, like, so you must be in a position, at least when you are studying conduction, to draw the temperature profile. Okay. Okay, Sanvi said, sir, please explain. Okay, sure. I'll be happy to explain. But yeah, you should speak up, right? Then only I can understand like you understood that or not. Okay. Yeah, but yeah, I'll explain it. Okay. Just hang on. Okay. So I'll make this system a little bit like nicer to see. And in that way, like it will make things clearer. Okay. All right. So let's try to understand the problem first. So what the problem says is that there is a heat generation that is being taking place in this slab. Okay. That's what this says. A one-dimensional plane wall of thickness twice L equal to 100 experience uniform thermal energy generation of 1000 watt per meter cube, and it is convectively cooled. See, this line is important. It is convectively cooled at x equal to plus and minus 50 mm, which means that at x equal to plus 50 mm here and at x equal to minus 50 mm here, okay, this plate having a predefined thickness where heat generation is taking place is being cooled. Okay, that is what the question has said to us. I'll underline the line convectively cooled. Okay, and then it says that if the steady state temperature distribution is T of x as a into L square minus x square plus b, where a is equal to 10 and b is equal to 30, then they're asking what is the thermal. So what they're asking is something different. Okay, but this is where up to which the problem has given us the information. Okay, So they have already says that the temperature profile T of x is basically equal to A into L square minus x square. Now my question was, based on this, if I want to sketch how the temperature profile look like, I said that it will be like this one line or like this curve that I said. And my argument was as follows. So first of all, you need to understand that what so from which phase, or what I said is that first of all you need to understand on which cross section is the temperature maximum. Okay, see, I'll give you a trick. Here, if you substitute T at x equals to 0, it will be what? It will be, so it will be A times L square plus B. Okay, can you tell me what is this value given that A is equal to 10 times L square? So so your L is 50. So your L square becomes 50 into 10 to the power minus 3 squared plus B, and your B is 30 degrees. Can you tell me what is this quickly? Then I can make you understand in a much better way. Can you tell me? Um, so can you guys tell me what is this? Okay, let's just do it. I think I have a calculator here. I mean, I don't have a calculator at my end, but I don't know. Let's do it. 10 see, 50 into 10 to the power 3 is 5 into 10 to the power minus 2, which becomes 0.05 square. Okay, plus it's 30. All right, so this becomes, if I'm not wrong, this becomes 30.025 or something like this. Okay, which means at x equal to 0 at this point, yes. So which means at x equal to 0 at this point, my temperature is 30.025. Okay, now please be attentive and answer me that when I move either in this location or in this location, will my temperature be above 30.025 or below 30.025? Just by looking at the temperature profile and understanding how the physics of this problem works. Okay, can you tell me? Will it be above 30.025 or will it be lesser than 30.25? Just by looking at this temperature profile, when we move either in the plus x or in the minus x direction, will T of x be greater than this value or it will be less than this value? I mean, if you are confused, you can just take x equal to 10 mm. Okay, substitute it here and check it out. So if you see, I mean, if you just put these values, you will see that at each and every cross section, apart from the central line cross section, your temperatures will be less than 30.25. Okay, see, the profile also speaks like there is a minus x square here, which means either you go along the plus x or along the minus x. This minus term will decrease the temperature. Okay, then the temperature in the center line when x is basically equals to 0. That you can speak it from the profile. And that is typically the reason why your temperature at each and every cross section in this point will be lower than the center line cross section, which is 30.25. Now, why it's not a straight line and it's a parabola is due to the fact that it's x square dependence, and that's why I draw a parabola and not a straight line. And typically, you can solve it from the heat diffusion equation and reach out to the conclusion that whenever there is this heat generation, your temperature profile is essentially parabolic and not linear. Okay, now did you understand why this is the correct temperature profile and not the other way around? I hope you did understand, right? Okay, very good. Okay, thank you very much. All right, so now we'll be solving the problem, but this was the essential physics that I want to bring it out. Okay, so we'll be solving this now. So what do we first need to calculate? So we need to find thermal conductivity, right? So can you now tell me how do we calculate thermal conductivity? At least a try. Uh, Yes, energy balance. Yes, exactly. So we'll be using energy balance only. But Yes, we'll be using energy balance. That is correct. Okay. So what? So when we use energy balance, we'll just write E dot in minus E dot out. Okay. Plus the energy that is being generated, and this is equal to 0, as you have rightly pointed out. So can you tell me, will there be E dot in this system? In this system. So first of all, you need to pick the control volume. Our control volume we will choose to be this slab. Okay. And in this slab, will there be energy that is going in, or will there be energy that is coming out, or will heat be going out of the system, or will heat be coming inside the system? It's simple, right? Because the slab is losing its energy, losing its heat to the surrounding, which means whatever the heat that is being generated in the slab must be dissipated out to the surrounding, which means this term E dot in has to go out to 0. Okay, which says that whatever the energy or heat that is being generated inside the slab will be dissipated to the surrounding. And you can show that if you simplify this expression. I'll not show you the steps. The steps you can see it in the theory class. This equation simplifies to a very famous, I mean, the energy balance simplifies to a very famous equation in conduction heat transfer, which is known as the heat diffusion equation. Okay, and the heat diffusion equation, okay, the heat diffusion equation will essentially translate to be d2t by dx2 plus q triple prime by x is equals to 0. Okay, so I think you guys have seen this equation many a times in this year's, I mean, in this week's theories. So this is basically the heat diffusion equation. I again repeat, if you apply this energy balance equation, and after some time I'll show you a trick from where directly you can get the answer from applying this equation alone. But if you follow the theory, it says that if you apply this energy balance, and if you just substitute the value of E dot out and E dot generated, okay, and see, this E dot out essentially comes from the Fourier's law. Okay, the Fourier's law says that it is ddx of k times dt dx. Okay, and with the area. And that's why this simply comes out at d2t by dx square. I hope you are on the same page with me when I say this. Okay, just look at the derivation of this heat diffusion equation. But yeah, it essentially comes from this energy balance alone. Okay, which means, so now what do we require? We require k, right? And your temperature profile is known. Okay, your temperature profile is this, that is given to us, which means you can find out what will be d2t by dx2. So can you tell me what is d2t by dx2 from here? What is this d2t by dx2? Given that this is your temperature profile, can you give it a try? So this easy, right? So dt by dx is what? Dt by dx is minus 2 times ax, and d2t by dx2 is equal to minus 2 times a. Yes, minus 2a. You were right, Sanvi. So this becomes minus 2 times a plus this q triple prime or q dot. Okay, this q triple prime is basically the, okay, I'll just write it as q dot because it's given as q dot in the problem. This q dot is basically the volumetric heat generation, which is 1000 in this case, and this is of course k, and this is equals to 0. So if you solve for this, your k would be 1000 divided by 2 times a. Your a is given to be equal to 10, which means it is 1000 divided by 20, and it is equal to 50 watt per meter Kelvin. So that's the first answer. Okay, so I hope you also got this answer. All right, so this is the first answer that the question has asked us. Okay, to calculate the thermal conductivity based on the fact that by using this energy conservation principle. Now can you tell me, if you guys understood, how do we calculate the heat transfer coefficient from here? So this is the calculation of thermal conductivity. Now you need to tell me, how do we calculate the heat transfer coefficient? Any idea? We solved this actually in the last class when we used that pipe, that steam coming out through a pipe, and we said that the energy that is being dissipated from the pipe will go into the ambient. Okay, and there's something that we did there. Can you tell me? Okay, so I'll show you how to calculate the heat transfer coefficient. Just try to understand. Now, what we will do is, in order to calculate the heat transfer coefficient, we will try to take either this phase or this phase. Okay. So always remember these interfaces. So this interface is between this ambient fluid and the slab. Okay. And interfaces cannot store energy. Okay. Which means whatever the energy that is coming from the slab to this interface has to go out from this interface to the fluid. Okay. So I hope you understood what I said. So if we apply the energy balance principle at the interface, it says that whatever energy that is coming out on this interface should be equal to the energy that is going out from this interface. Okay, now you need to tell me what is the energy, or what is, so energy means it is the flux multiplied by area, but the area of this interface, if we see from this side or this side, is basically the same, which means that the flux that is coming out from this side is equal to the flux that is going out from the interface to the ambient. Okay. So what I am trying to say is that at x equal to, let's say, L, okay, you can choose minus L also, that's completely up to you. So at x equal to L, the flux that is coming out from the slab to this phase is equal to the flux that is going out from this slab, from the interface to the uh, ambient fluid. Now can you tell me what is the flux that is coming out from that, I mean, that is coming onto the interface from the slab? Can you tell me the expression of this flux? Is it, first of all, is it a conductive flux or a convective flux? Or, so we are not considering radiation. So is it a conductive flux or a convective flux? So if I write this, you just need to tell me, is this correct or right or wrong? Yes. So, so what is this flux? Is it a conductive flux or a convective flux? Can you tell me? So this is a, yes, this is a conductive flux. Exactly. See, this is a conductive flux. And before me explaining it, can you tell me what is this? Is this a, what is this? Yes, it's a convective flux. Very good. So this is a convective flux, and this is true. And as I said, this is true because when we look onto this interface, okay, so try to understand what this interface sees. So when I sit on this interface, let's say, it says that, okay, there is a energy, or there is a heat that is coming out from this slab to me, and since these interfaces cannot store energy, I must dissipate this heat to the ambient, right? Which is basically the convective flux. So the mode of heat transfer from the slab to this phase is basically conduction, and the mode of heat transfer from this phase to the ambient is convection. And that's why the heat flux, and since the heat flux is a constant value, I can write that minus k dt by dx is equal to h times t at x equal to L minus T infinity. This comes from the Fourier's law, which is basically the conductive flux, and this comes from the Newton's law of cooling, as I have said, when we do convection heat transfer. Okay, now you can see that everything is known here. Dt by dx at x equal to L is known because the temperature profile is already known. This k we have already evaluated. Okay, and this t at x equal to N minus T infinity, we have already evaluated that. So which means you can just write down the expression of H, which is the heat transfer coefficient, as minus k times dt by dx at x equal to L is, and this divided by t at x equal to L minus T infinity. So all these things are known. This thing is known from the temperature profile. You can evaluate this from the temperature profile. Thermal conductivity we have already evaluated. T infinity is given to us, which is equal to 20 degrees Celsius. Is T infinity is given to be equal to 20 degrees Celsius. From this, if you do the math, you will get the heat transfer coefficient as 5 watt per meter square Kelvin. You can check it out by yourself and you can do this. Okay. So I hope this is clear to you. Like, how did you calculate the heat transfer coefficient? But more important is you should understand how did we write this. Basically, this is known as boundary condition at the interface. Okay. So did you understand this boundary condition? I'll ask and I'll be happy to explain it again. But did you understand this or not? So this is the conductive flux, okay? And this is the convective flux. Yes, very good. Okay. Now I'll end this. So this is the last problem that we do. I mean, we'll not stick to more problems. I have one more problem, but we'll do that in the next week. Let's not like stretch it too long. I will end the class by showing you a shortcut way. I mean, it's a shortcut way based on the energy balance principle, as Sanvi has said. I'll show you that in one line only you can calculate what will be this convective heat transfer coefficient. Okay, and you will be really happy to see this. Okay, so let's do this. I hope this problem is clear. Now I'll show you a easy way, or like in competitive exam, you need to apply these kind of procedures in order to get the heat transfer coefficient. Okay, but for thermal conductivity you really need to use this heat diffusion equation that I basically said. Okay, and in fact this heat diffusion equation is a simplified form of this energy balance principle only. But if people ask you directly to evaluate the heat transfer coefficient, I'll show you a very easy way. Okay, so from the energy principle, what did we find out? We found out that whatever the energy that is being generated is equal to the energy that is being going out from the control volume. So far so good, right? So let's try to quantify what is the energy that is being generated inside the slab. Okay, so we need to be little bit clever here in trying to find out what is the energy that is being generated. So what do we know? We know that so what do we know inside the slab? We know that the amount of heat generation inside the slab is given by Q dot, and it has a magnitude of 1000 watt per meter cube, which means, can you give me a hint by which, knowing Q dot, I can evaluate what will be the energy that is being generated? Can you tell me? So can you write, or in other words, can you write this E dot in terms of Q dot and some other parameters? Okay. So I hope you got my question. Can you tell me? So what is E dot generated in terms of this Q dot? Yes, exactly. You are exactly right. And this is how actually essentially we should think about why we how we could have solved this problem in very simplest way. Okay. So as Sanvi has rightly pointed out, energy generated is basically Q dot. Oops. So it basically Q dot multiplied by the volume of this thing, right? The volume of the slab. Okay. And this is given to us, right? Because Q dot into volume is basically the cross section multiplied by twice L. Okay, that is simply because the cross sectional area we could take it to be A, and this length is given us as twice L, which means this this E dot generated, okay, this E dot generated is equal to Q dot 2Q dot times A into L. Okay, this is one thing. Now, can you also quantify me what is the energy that is coming out? So this we have already seen 2 steps back. Can you tell me what is E dot out? I mean, you did excellent in like evaluating what is E dot gen. Can you tell me now what is E dot out? The hint is again that Newton's law of cooling. See, I'll tell you, the hint is this. The hint is this. The only difference is we wrote this flux. Try to come out with how this would look like when we write this in terms of energy or the rate of heat transfer. Just one thing that we must add here, okay, that will basically, so how this quantity will transform into, so this is watt per meter square, right? How this will transform into watt? So what should we add here to make this into watt, from watt per meter square? That's the answer. Can you think of that? Yes, exactly. So that's the area, right? So this means that E dot out, okay, that E dot out, that E dot out is, so E dot out is nothing but the convective flux, right? That's what I have been repeatedly saying in the previous like exercise, that whatever the flux that we have here, this must be dissipated to the surrounding. And the only way it can dissipate is by convection, right? Because we are ignoring radiation heat transfer here. Okay. And that convection flux or the convection heat transfer is nothing but the heat transfer coefficient multiplied by area multiplied by temperature at x equal to L minus the ambient temperature. That is something that we again did here. Okay. That is something that we again did in this like exercise. So if you equate these two, okay, let's equate these two. So what do you get? You get 2 q dot al is equal to HA times T at x equal to L minus T infinity. Your area and area cancel out, which means your heat transfer coefficient, okay, your heat transfer coefficient is 2 q dot by T at x equal to L minus T infinity. And you can substitute these values and exactly find out that your answer would be just this 5 watt per meter square. You can check it at your home and you can verify that your answer would be exactly same as 5 watt per meter square. Okay, just verify this at your end. Okay, so did you understood this like the shortcut concept or not? And now, yes, very good. And just before ending, as I said, I'll just clarify you all. As I said that this heat diffusion equation essentially comes from here only. I'll just show you in 2 steps just to make the things complete. Okay. I hope you are on the same page with me. See, this is very simple. When you write this E dot out, okay, this E dot out is what? It is the flux. It is the flux that is moving out from the interface. Okay. And what is this flux? This flux is the conduction flux, right? So this E dot out is essentially minus this q dot conduction okay times the area, right? And this q dot conduction is nothing but minus k dt by dx from Fourier's law. So when you just substitute this, okay, when you just substitute this and you just put it in here, okay, and then you need to calculate E dot out. In principle, you will end up getting this same heat diffusion equation. Okay, so this so I just gave you the hint of how did we get this heat diffusion equation from this energy balance. But yeah, for more like for a detailed derivation, you can refer to the lecture videos of this week. It is in detail shown it there that just applying an energy balance, you end up getting the heat diffusion equation. But this is how actually you need to solve when you are solving it in pen paper. But in a competitive exam, like when you need to, so in competitive exam, they will just ask you to calculate the value of h. Okay, given this information, they will just ask you to calculate the value of h, and there you can just apply this this shortcut trick that balancing the fluxes at the interface will solely give you the value of the heat transfer coefficient. Okay, which is basically this. Okay, so is this clear or not? Like can you tell me you understood this, or like is there something that that uh, that that is still left to be explained, or so far like you understood this problem? Can you just give me an yes or a no? Yes, very good, Sanvi. So just one thing, and then I'll finish. Okay, I'll just ask you a simple question, and then I'll finish. That's for your exercise. That so this is your take home, or if you can answer it now, it's very good. But it's your take home kind of thing. Okay. So this is a slab. Okay, this is a slab. Okay, this slab consists of two materials. One material is A, and the other material is B. And here I draw something which is the temperature profile. Okay, for instance, when I move, let's say this is my axis and this is the positive x-axis. Okay, and in this context I draw my temperature profile. Okay, so this is one temperature profile and this is another temperature profile. Okay, so this is basically the temperature profile. And I say to you, as it appears from the sketch, that the temperature profile is linear. Okay, now just tell me one thing, that is thermal conductivity of A greater than thermal conductivity of B, or is thermal conductivity of A equal to thermal conductivity of B, or is thermal conductivity of B is less than thermal conductivity of A? If you can answer this, think about it, and if you can answer this, rest assured you have learned conduction heat transfer 80%. Okay, like there is nothing more physically that you need to learn in conduction heat transfer. From now on, what we'll do is an extension of what you already learned. Uh, like from so So conceptually, this is something that you should answer. Okay. So can you think about it? So this is something that I'll ask you to think about it. If I'll give you 2 minutes, if you can 2 minutes, I'll give you 5 minutes. If you can just come up with the answer, you can tell me, or else think about it and we'll do it in the next class. But the answer is just two-step answer. You just need to think. So I'll give you the hint. You just need to apply Fourier's law and think about in what case does the temperature profile becomes linear. Okay. Uh, do you like to give the answer or you need some time? It's okay if you can take some time. I'll give you a couple of minutes. The hint is this: the temperature profile is linear. That's the main hint. And what do you know is you know these things. So try to think what is the difference that differentiates this material A from material B. Okay, and this is your temperature profile, of course. It has some temperature here, it has some temperature here. Okay, so just think about it. Uh, I'll not say you the answer now because it because I wish that you like try to think about it and come up with the answer. Okay, you can post this answer in the discussion forum. Okay, and if you come up with the answer, you can post it in the discussion forum. We'll see how many people can try to answer this or not. Okay, in fact, this is one of the famous question. Not sure, but yeah, okay. Sanvi said is not sure, but K equal to KB. All right. All right. But this is a very famous question people ask in GATE examination, okay, in mechanical engineering. All right. So it's not so okay. I'm very happy that you give it a try, but K is not equal to KB, okay? And since you have said the answer, and sorry, since you have gave it a try, I'll say what the answer is, okay? See, the main hint is that the temperature profile is linear. And in the last class, I repeatedly said that under what condition the temperature profile becomes linear, okay? One case is that whenever the heat flux is constant, then temperature of profile becomes linear. That's typically because when I say T is a linear function of x, this means dt by dx has to be constant. And dt by dx is nothing but the heat flux. So if my temperature profile is linear, this means at least in 1D heat transfer when thermal conductivity is constant, you can say that heat flux is constant. So for this problem, your Q double prime, which is the heat flux in x direction, this is constant. Okay, so you can write that your flux Q double prime of x is constant. All right, so this flux, how can we write? So we can write that flux is what? Minus Ka times dt by dx for material A, because since your flux is constant, whatever cross section you pick out, your flux has to be the same value. Okay, so I pick out two cross sections here. Okay, one cross section is in material A, where I can write the flux as Ka times dt by dx of material A, of course. dt by dx of material A. Now, if I pick out another cross section here, okay, I can write the flux as minus Kb times dt by dx at P. Okay, so this minus and minus sign you can just cancel out, and you can see from the figure, that, can you tell me dt by dx of A is greater or dt by dx of B is greater from this figure? And try to understand what is dt by dx. It is just the slope of the temperature profile. So dt by dx of A is greater or dt by dx of B is greater? Can you tell me whose slope is greater? Yes, B is greater, which means now can you tell me, is KB greater than K or KB less than K? If this is greater than this, then what happens to this and this? If these quantities are equal, it should be, so give the answer. So what should be the answer then? Yes, B is greater, exactly. B is greater. No, dt by dx of B is greater. Then what happens to KB? Can you tell me? So you partially gave the answer. No, right? See, See, these quantities are equal. Okay, I'll write that again. Okay, I mean I think I'm messing up with my this drawing, so sorry for that. So Ka times dt by dx of A is equal to Kb times dt by dx of B. Okay, and we are writing this because heat flux is constant throughout this entire like slab or whatever you consider. Okay, now you said that dt by dx of B is greater. That is evident from this diagram because this slope is greater than this slope. Okay, so if this is greater and if these two quantities are equal, then so if this is greater than this and these two quantities are equal, this has to be less than this, right? I mean, did you get it? So if dt by dx of B is greater than dt by dx of A, and if these two quantities are equal, then Kb has to be greater than Ka. Okay, so that's the answer. Did you understand, Sanvi? I mean, did you understand this? This constant. Okay, sorry. Sorry. I mentioned one thing wrong. I mentioned one thing wrong. What I am saying is okay. I understand. Okay, I understand your doubt. Sorry for that. I actually made a like when I was saying I actually made a mistake here. So I'm not saying dt by dx is constant. I'm saying that heat flux is constant. Okay, all I'm saying is that your heat flux, this q double prime of x, this is constant, and your heat flux is thermal conductivity times the temperature gradient. Okay, I'm sorry for that. Like I just said by mistake that dt by dx is constant. I'm saying that heat flux is constant. Okay, and in 1D case, heat flux like in 1D heat transfer case, heat flux तभी constant होता है when the temperature profile varies linearly. But this does not ensure that your dt by dx for two different medium will be the same. Okay, did you understand? Uh, okay, yeah. Thank you very much. And actually, this problem is exactly similar to the one that we solved only, but I summarized you the problem. So let's not go into the next problem. It's essentially the extension of this problem only, but yeah, but I just summarized you in this problem. So I hope you have understood this problem and the subsequent problems that we solved before. We'll not solve any problem now, but since we have some time, I'll wait here for a couple of minutes. If you have any questions throughout the entire problems that we solve, you can ask me. Or if you have any questions based on the other problems that we solved in the last week or on the assignments, you can ask me. Or else we'll call it a day today. Yeah. So I'm sorry for the confusion that I created. When I say, so always remember, when I say that your temperature profile is linear, this means that your heat flux is constant. Now, since had this been the case that this is a single material instead of it being two material, then I could have said that your dt by dx would also be constant. But since here it consists of two materials, then and these two materials have different thermal conductivity, I cannot say that dt by dx is constant. And in fact, dt by dx essentially varies, right? Varies means when we move from material A to material B, the slope of dt by dx changes. Okay, but heat flux has to be constant. See, this is something that you can again prove. Just take this uh, entire like slab as the control volume and apply energy balance. What you will get is E dot in equal to E dot out, which means that the rate of heat transfer is constant. And since the areas are same here, that means the heat flux is constant. Okay, and based on this information, apply Fourier's law, and you can come with the relation of dt by dx of B and dt by dx of A. Now, am I more clear now? Like, am I making sense now? Uh, did you get it, Sanvi? I hope like you understood this now. And still, if you have any questions, you can ask me, of course. Okay, I hope you understood this. I hope you like understood this. I hope so, sir, but what? Okay, so you have a question. Okay, let's see. Okay, sir, but what should we understand by heat flux? Okay, so your question is, but sir, what should we understand by heat flux? I know technical, but generally asking. Okay, yeah, that's a good question. So your question is that how do we physically infer heat flux? That is something I think that you are asking. Okay, so see, when you say something about flux, any quantity, whenever there is a flux associated with heat, it becomes the quantity divided by the unit area through which we are calculating that quantity. Okay. For instance, if you say heat flux, that means if there is a phase, let's say my hand is a phase, that means per unit area of my hand, per unit area of my hand, if there is an energy, energy transfer that is taking place, what is that energy per unit area will say the flux. Okay. For instance, there is something which is known as momentum flux. There is also something which is known as mass flux. Okay. So for instance, I'll show it here. So for instance, let's say if I pick a generic surface, okay, let's say I pick a surface. Okay. For instance, this is a surface in space. Okay, let's say this is a surface. The dash line is a surface. So what flux says is that if I have a quantity that is coming out or moving in from this surface, let's say the quantity could be anything phi, then flux means this quantity which we denote the flux by double prime. The flux means this quantity divided by any elemental area that we choose here. Okay, this quantity divided by dA will denote the flux here. Okay, now this quantity can, so if this phi becomes heat, then this becomes q double prime, which is the heat flux. If this phi is mass, then this q double prime is mass flux, and so on and so forth. Which means you can write, so you can always write a quantity which let's say which is phi, which can be mass, it can be momentum, as the flux times the elemental area. And if we integrate this, okay, if you integrate this throughout this entire area, you get the entire quantity, let's say the mass, the momentum, or the rate of heat transfer. Like, is it clear? Like, what do you physically mean by flux? Okay, it's not always that you tend to associate flux with heat. There can be mass flux, there can be momentum flux. For instance, if I pick this elemental area, okay, and I pick the amount of mass that is flowing out through this area, okay, then the mass flux is this elemental area multiplied by, sorry, the mass that is coming out from this surface is the mass flux multiplied by the elemental area. Okay, and so on and so forth. Similar analogy can be drawn to momentum or the other quantities. Did you get a little bit physical idea of flux? Okay, thank you. I mean, I'm happy that like you understood uh, what essentially mean by the flux quantity. But yeah, okay, guys. If you don't have any other questions, so any other questions, you can just type or you can just unmute yourself. And if you don't have any other questions, like we will stop it, we'll call it a day, and then we'll meet in the next week, of course. Okay, so if you don't have any questions, thank you once again for attending this session. I hope you enjoyed solving the problems in this session, and I assure you that it will immensely help you in understanding this subject in a much better way. Try to develop conceptual clarity on these. So for these kind of problems gives you much more conceptual clarity, right? You have something known as flux. Then you say that okay, flux is constant, but the temperature gradients are not constant because you have two different material. Okay, and then try to come up with a relation of thermal conductivity, and then like understanding these kind of problems where you kind of tend to develop the idea of essentially drawing a temperature profile. Okay, this idea is very much important when you study heat transfer. Okay, so all these things, I hope you have clarified a much more in this session. And if you have any doubts, always post it in the discussion forum, or you can ask me in the next class. Till then, like, thank you very much. Thank you for attending this session, and it's okay. I'll call it a day now. Thank you very much.